Hello everybody. In this section we want to compute the area of a region which is bounded by two curves. In this example we want the area between the black and the red curve over the interval from A to B. With our old technique we would need to compute three different integrals. One for the area below the upper black curve, and two for the two areas bounded by the lower red curve and the x-axis. But actually, one single integral will suffice. To understand this new technique, let's go back to the slice and sum strategy. Remember how this goes. We partition the interval from A to B into subintervals. On each of them, we build a rectangle. What's new is that this rectangle extends now from the lower curve to the upper curve, and not just from the x-axis to the upper curve. As always, the width, delta x, of each rectangle is given by this formula. Then the area of each rectangle is delta x times the height of the rectangle. And this height is a difference of the upper and lower function evaluated at a point xk on the subinterval in question. Why does this difference give the height? It should be clear that this is true when both f of xk and g of xk are positive, like in this rectangle. If the upper value f of xk is positive and the lower value g of xk is negative, like in this rectangle, then we take into account that the negative of a negative is positive, so the difference actually adds up to the correct height of the rectangle. Please pause the video for a moment and convince yourself that you understand this and a third case, which is not illustrated in this picture. Even if both values are negative, we will get the correct positive height of the rectangle. We only need the black function to be on top of the red one on the entire interval. The next steps are exactly as before. Add up all the areas of the rectangles and go to the limit. But this is the definition of an integral. The text in the box sums up this discussion and provides an area formula. Note that you can only apply this area formula under two conditions. The functions f and g must be continuous on the interval, and f must be bigger or equal to g on the entire interval. In the first example, you have to find the region bounded by the graphs of two functions f and g and by the y-axis. It is, of course, always helpful to look at the graphs. In this case, we see that the lower limit of the integral must be 0, as the region is bounded by the y-axis. In order to get the upper limit, we need to work a little bit. To the right, the area ends at the intersection point of the two curves. We need to compute this intersection point. In this example, this leads to an equation of degree 3, and for these, you are allowed to use the root finder of your calculator. It turns out that the curve intersect at x equals 1. Then you just substitute f and g into the area formula. In this example, the authors of this text employ a fact which you don't know and don't need to know at the moment, namely that the antiderivative of 1 over 1 plus x squared is the arctangent. Then it is just the fundamental theorem and evaluating. Please stop the video now and work on the two exercises 5 and 14 on page 89. In some cases, you still need to use more than one integral. This goes under the name of finding the area of compound regions. Compound here means made up of several ingredients. In example 2, you have to find the region between a linear function and a function which involves an absolute value. In order to do this, you need to know that in order to compute the absolute value of 2x, you have to distinguish two cases. The absolute value is plus x, plus 2x for positive x, and minus 2x for negative x. Here is a picture. So you have to evaluate these two integrals here. Please stop the video again and study the details of this example on your own. Afterwards, work on the two exercises 19 and 20 on page 89. Sometimes a curve cannot be expressed by means of a function with the argument x. For instance, in this graph, there are some values of x for which you would need 2 or even 3 y values. The trick is to reverse the roles of x and y. Instead of assigning a y value to each x value as in ordinary functions, we assign an x value to each y value. This gives us a function x equals f of y. So the y-axis takes on the role of the x-axis and vice versa. If we want to compute the area between two such curves, we can use the same slice and sum strategy as before, but now we slice horizontally, not vertically. What does that mean in practice? We partition an interval on the y-axis, here from C to D, and we construct rectangles that extend from the left curve to the right curve. Now the height of these rectangles is delta y, and the length is the difference f of yk minus g of yk. For this, we need f to be to the right of g on the entire interval. We get the same formula as before, only with y, and with the limit c and d of the integral now lying on the y-axis. In the text, they do example 3 in two ways. First, they integrate in the usual fashion along the x-axis, which needs two integrals. And then they compute the area again by integrating along the y-axis, which only needs one integral. In both cases, you start with computing the intersection point. To integrate along the y-axis, you first have to express the two functions with the argument y. In practice, that means that you have to solve the equation of each of the two functions for x. So the cubic function y equals x to the power 3 transforms into the root function x equals y to the power of 1/3. And the linear function y equals x plus 6 transforms into another linear function x equals y minus 6. Then you can simply use the area formula. Please stop the video again and do the exercises 29 and 32. In the last example 4, we have to find the region between a root function and a linear function. We can either slice the region horizontally as in example 3 and integrate along the y-axis. Computations are done in the text, or we think geometrically. First, we calculate the complete area below the root function in the usual fashion by integrating along the x-axis, and then we only need to subtract the area of a triangle. For this section, please do the two exercises 33 and 38, and then finally do the exercises 55 and 61. Thank you for watching.